Hello, everyone, and thank you for joining us today for this session of LC-MS 101, The Fundamentals. Today, we'll share knowledge around the fundamentals of both chromatography and mass spectrometry, as well as explain key terms and analytical techniques associated with this technology. I'm 𝗞𝗿𝗏𝗀𝗲 with SCIEX, and I am your moderator for today. And today, I am joined with our speaker, Dr. 𝗞𝗿𝗏𝗀𝗲. Thanks for joining, Carl. Dr. 𝗞𝗿𝗏𝗀𝗲 is a senior scientist driving food, environmental, forensic, clinical, and cannabis applications at SCIEX. Before joining SCIEX, he completed his PhD at Colorado School of Mines in hydraulic science and engineering, where his research focused on non-targeted characterization of complex surfactant mixtures, including aqueous film-forming foams, which led to the discovery of several novel per- and polyfluorinated alkyl substances, also known as PFAS, that since have been found in a variety of environmental samples and industrial chemicals. Since joining SCIEX, Carl has worked with numerous labs, creating and implementing both quantitative and qualitative methodologies. Thank you again for joining us. We hope you enjoy the presentation, and I'll turn it over to Carl.
Thank you so much, 𝗞𝗿𝗏, and thanks everybody for being here with me today. So today we're going to be really talking about some of those fundamentals. So the way I kind of designed this talk was to focus on folks who maybe are new to mass spec, or someone who has been doing some mass spec and just wants to kind of refresh on some of the key variables in mass spectrometry. So if we just take off our science hat for a moment and think about how just the general public interacts and views mass spectrometry. So probably friends, family, they might be familiar with mass spectrometry, maybe from something like a TV show. And in fact, if you have told anyone you're a chemist within the last, probably say about 7 years, they'll probably responded with, oh, like Breaking Bad. And that's fair. They did use mass spectrometry in Breaking Bad to test the purity of methamphetamine. That's true. But mass spectrometry affects our lives in a variety of ways beyond just testing drugs in a fictional TV show. It impacts everything from studying previous cultures to understanding if there's life beyond Earth, keeping us alive when we go under anesthesia, and all the way down to keeping our food safe for our pets and family and friends. So regardless of whether you're a chemist or you're just a regular person out in the grocery store, mass spectrometry affects our lives every day. So the first thing we're going to be talking about is really this separation. So before we get to the mass spec, we're going to talk about the LC portion. So this is really where this separation comes into play. And in our next session, we'll dive into some of the specifics, but here let's just kind of introduce some of these ideas. So in 1906, a Russian botanist first developed chromatography, and he was really interested in plant pigments. So he's looking at pigments in plants, and that's kind of where chromatography gets its name. So it's Greek for color writing. And since that discovery, it's really branched into two specific fields, or at least when we talk about organic analysis, two main fields, GC and LC. So obviously this presentation is going to really focus on LC, but maybe you've been familiar with GC. I know when I first started, I did a lot of gas chromatography. So maybe you're switching over, and let's just kind of touch on some of those key differences between gas chromatography and liquid chromatography. So the main difference that I would like to kind of instill is when we talk about gas chromatography, we really need our compounds to be volatile for that to be a reasonable approach for us to use. Versus liquid chromatography, we need those compounds to be soluble. So that's the really distinguishing factor of whether we're going to go with a gas chromatography or a GC approach versus an LC approach. Additionally, some kind of other interesting little facts. For GC analysis, typically we're talking about relatively small compounds. Most of the time we're talking about sub 500 Daltons. So my background is in environmental science. So that's kind of the area that I deal in. But I know many of you study things like polymers and proteins that are much, much larger. So GC might not be a great approach for those larger compounds. It really isn't. Compared to LC, where we can look at some of these really large compounds. So talking about things that are 100,000 Daltons instead of just 500 Daltons. But regardless of which approach you take, which one's right for your sample, both are really quantitative, they're both robust, and they're both reproducible. They've been around for a long time, and we use them all the time in the lab to complement each other. But let's get into LC. So what makes up an LC? So let's start with the top. First, we have our mobile phases. So we typically have two mobile phases. Our first mobile phase would be mobile phase A. This is typically some sort of aqueous mobile phase. And a second mobile phase, which would be commonly referred to as our organic or mobile phase B. And the way we're going to introduce these mobile phases into our system is via a pump. So I just drew a little diagram of a binary pump system here. So when I say binary pump, all I mean is that one pump is for the organic, one pump is for the aqueous. So from our eluent bottles, we have our mobile phase moving into our degasser. And our degasser is simply doing exactly what it sounds like it's doing. It's removing gas. So maybe previously you've seen people in the lab sonicate eluent bottles to get the bubbles out. With most modern systems now, we can just rely on this degasser to get those bubbles out, so we don't have to do that extra step. It's then moving its way into the mixer, which is again doing exactly what it sounds like it's doing. It's mixing our two mobile phases together. And this is really important though. We want to make sure that we're mixing consistently and we're mixing accurately. So typically these mixers are pretty small in size, somewhere between 20 and 100 microliters, depending on your application. So once we move past this step, our mobile phase is going to make its way into our autosampler. And just like any other autosampler, this is really just saving us time, right? I know when I first started doing analytical chemistry for my master's, there was a instrument I needed to use and we didn't have an autosampler. So I had the luxury of sitting there with a stopwatch and every 20 minutes injecting a sample. So it's come a long way and it's great that it has. So what we're doing is we're withdrawing some of our sample. For LC-MS analysis, we can do anywhere from around a microliter all the way up to a milliliter and above, depending on what kind of your method is and your approach and what detection limits you need. But regardless, we're loading that sample into our sample loop. And from there, once our valve switches, our mobile phase is going to push our sample out of that sample loop and introduce it to our column. And our column or analytical column is really where all the magic and separation is occurring. So we store that column within the column oven. And the reason we're doing that is just to make sure it's at a consistent temperature. As we increase temperature, typically what we see is a decrease in column pressure. And also our analytes are going to move a little bit faster through that column. So I'd hate to see, a column be outside of a column oven and then your AC kick on and your room gets a little bit colder. That's going to mess with your retention time. So keeping it in a column oven, a little bit above your room temperature is usually what I would recommend. But our analytes are passing through that column, and this is their chance to really interact with that column in some way. So what we're going to want to do, or what we're going to want to, how we're going to want to choose a column rather, is to have the analytes of interest interact differently than the analytes we're not interested in. And a really easy example of this would be salts. Salts are a mass spec's worst enemy. We don't want to introduce them to the mass spec. We wouldn't be able to analyze them anyway. So an HPLC column or just an LC column, there's going to be really no interaction there with salts. So they're going to immediately just pass through a column while our analytes of interest are interacting with the stationary phase, and we can divert that to waste. But how our analytes interact with that stationary phase is going to depend a little bit. And it depends on a few factors. So here I have an equation for chromatographic resolution. And in the bottom, in the red box, we have a lower resolution image, and in the blue box, we have a higher resolution image. So what we're trying to do is separate our peaks. With MS-MS, this is not as important as, say, UV. With UV analysis, if our peaks were superimposed, there's not much we can do in terms of integration and quantification. We really need to separate them. Whereas with MS-MS, we can kind of get away with this a little bit. But regardless, we're always trying to keep separation between our peaks. And the variables that we do or use to do this, one would be efficiency. So efficiency is the number of theoretical plates and kind of describes that chromatographic band. But instead of thinking about it as a definition, I would rather us think about it as what factors are controlling that variable. So when we think about efficiency, some of the factors that really have an influence on that variable would be column length. So the longer a column, typically they're anywhere from 50 millimeters to 150 millimeters for just traditional HPLC analysis. The longer that column is, the longer it's going to take your analytes to move through that column. And that's a good thing. We'll have more resolution, right? As the column length increases, our resolution increases, but it comes at a cost, and that cost usually is time. So if you have a 20-minute method and using a longer column means you only have to add 1 or 2 minutes to your method, that might not be a big deal. But if you have a really short method, maybe 3 minutes, 4 minutes, adding a couple minutes it's a big difference. It could double the length of your minute or your method. So that's something you kind of have to consider. The same with particle size. So the way I like to think about particle size is with a larger particle size, we'll have sort of wider peaks. And with a tighter particle size, we're sort of sharpening up those peaks. So we're increasing that area, or we're increasing that height of the peak, essentially increasing the sensitivity, which again, great. Some of the drawbacks or some of the compromises you need to make when you go to a smaller particle size would be column pressure. Make sure your LC can handle that sort of pressure. And also, if you have a really nasty matrix, I'm going to be talking about cannabis a little bit, which is just a truly awful matrix. The smaller the particle size, the more risk you have for running into things like clogs. Next would be retention. So retention is really controlled by your mobile phase. And that's just the amount of column volumes it's going to take for you to have your analyte of interest elute. So for LC-MS analysis and HPLC analysis, we really focus on sort of like 3 major solvents. Our aqueous, water, and methanol and acetonitrile are the next 2 common solvents that we use in terms of an organic. And they're going to affect when your compound elutes a little bit differently. So there's a little bit of wiggle room there in terms of what you choose as your mobile phase. But probably one of the most important factors, and if you look at that graph, you can kind of see it's one of the most important variables for chromatographic resolution would be your selectivity. And this is really your stationary phase and how your compounds of interest and your compounds that you're not interested in interact with your column. So during the the method development section, we'll kind of dive in deeper into specific column stationary phases. But for now, I just kind of want to introduce some of the properties they're using to interact with that stationary phase. So some of the more common techniques that are used would be hydrophobicity. So this is great for neutral compounds versus something like a steric influence. And a steric influence is really more dependent on your compound structure. So different structures will interact differently with that stationary phase. You can then get into something like an H bonding and H donating, H accepting and H donating capacity. And those are going to work for different compounds. For an H donating, we're talking about sort of amines and amides, more bases, versus H accepting, which we're talking about more acids. But regardless, we really want to choose a column that works for your analytes. So this can be, and admittedly it was for me when I first started, one of the more tricky parts of LC analysis, choosing the column that's right for your method. So there are a lot of really cool tools out. I particularly like this one from Phenomenex called Column Match, not just because it has a funny name, but you can actually enter in the structures of the compounds you're interested in, and it will give you suggestions on what stationary phase might be best for that type of analysis. But here would be a typical sort of chromatogram. So we have our peaks of interest. So all those colorful peaks represent individual analytes. This would be called an XIC or an extracted ion chromatogram. We're looking at a specific experiment, specific transitions, and we'll talk about those experiments in the next couple slides. And in blue, we have our pressure trace. So our pump B pressure trace. And if you remember from the earlier slide, that would be our organic pressure trace. And the reason I show pressure trace instead of just percentage is because our pressure for pump B really correlates or is directly related to the percent B. So as we see the pressure increase, we're introducing a higher amount of organic into our system. So a typical chromatogram or a typical LC gradient would have 4 phases. The first phase, we would start at a lower aqueous phase. So we're introducing more water. Sometimes folks would choose to skip this step. It depends a little bit on your matrix. I like to include it just because that water will really help rinse off salts from your column and kind of ensure that it stays clean. But depending on your matrix, that might not be of concern. Next would be our ramping phase. So this sort of gradual ramp where our compounds are actually eluting. So we're ramping from aqueous to organic. Our compounds are beginning to elute. And then once our last compound has made its way off the column, we'll hold it at a very high organic. And this is a really crucial step. So typically we want to hold it anywhere from 95% B all the way up to 100% B. And the reason we're doing this is to essentially wash off the column. And the time it takes to wash off the column is kind of related to that retention in the sense we're thinking about the same variable, how many column volumes it's going to take. So your column volume is related to your column dimensions. So the length, the inner diameter, et cetera. So we want to make sure we get at least 2 to 3 column volumes of organic through our column. And that's just going to ensure that all of those other analytes, the ones we weren't looking for, have washed off our column. We're keeping our column clean, and we can use it for many, many more injection. Once that step's done, we're going to do the equilibration phase, another really important phase, which again is related to the dimensions of your column. So we want to make sure we've gotten all that organic out of our column and are starting our next injection at the exact conditions we started our first injection. So if we choose to skip this step, what would happen is our column won't be equilibrated and our peaks will slowly start to creep up in our chromatogram. And we really want to avoid that and make sure that we have these steady retention times. So if we go back into the lab, we talked about our chromatography, we've injected our sample, it's gone through a column, we have separation, it's made its way to a mass spec, and now we get to do our mass spec analysis. So everything up until this point has just been us introducing the sample to our mass spec. Now we get to use the mass spec selectivity to actually quantify and use the data. But first, what kind of data does a mass spec give us? And in the simplest terms, the mass spec is really looking at a mass. We're reading a mass and we're getting an intensity at a specific time. And I say mass or molecular weight, but really it's a M over Z. So it's the molecular weight over the charge. And we'll go over what that means in a little bit and give some examples of that. But since we're talking about MS in this talk, we'll also have some fragmentation information. So how do we use this data and what kind of questions can we answer with this data? Because that's the whole reason we're doing it, right? We have a specific question and we want an answer to that question. And that question might just be how much. So we might want to use this data for quantification, which is one of the more common uses for mass spec or MS data. But we can also ask some more qualitative questions like what is this compound, and do some confirmation scans that we'll talk about to be confident, yes, this is truly the compound that I'm interested in. But before we get there, we got to start at the source. So how do we take from our LC this liquid and actually get it to move through our mass spectrometer? And to do that, we use ionization. So electrospray ionization is probably the most commonly used LC-MS ionization type. And it was invented in 2002 by John Fenn and some collaborators. And he was quoted as saying, he gave wings to molecular elephants, which is a quote I really like, because if we think back to that GC and LC diagram, for GC analysis, we're really talking about things sub 500 Daltons. And, folks that are interested in these large proteins, they might say, hey, I don't have anything below 10,000 Daltons. ESI really gives us the ability to explore that world. And for ESI, we're really talking about polar compounds. So we're talking about that polar to very polar range versus typical GCMS, where we're dealing with those non-polar compounds. And you'll notice I have another type of LCMS ionization there, APCI. So if you're from the environmental or maybe even the forensic world, you might have heard of APCI. And APCI, I like to describe as bridging the gap. So APCI allows us to look at some of the non-polar as well as some of the polar compounds. So it can be good for some of those historically GC compounds, but it really allows us to kind of cover this full spectrum of polarity. So how does it work? On the left, we have an ion source, and on the right, we have just a little schematic of how that ion source is working. So you'll notice in the image and the diagram, you see this capillary or this tube surrounded by two heaters. So our LC is pumping the solvent, our analytes of interest, analytes of uninterest, all through this capillary, and that capillary is essentially making a spray. And one of the things that's really important in LC-MS analysis is that we have a good spray. So if we think about, standing outside on a hot summer day with a hose, and we were just to open a hose and hold it upside down and just let the water pour out of it, we'd have a big puddle on our driveway. Versus, at least where I live in Colorado, where we have 10% humidity often, and it's super hot in the summer. If I were to put my thumb over that garden hose and create a really fine spray, I wouldn't run into the same issue. So we really want to make sure we're having a consistent conical spray. So we are spraying our ions and we're applying a charge. The charge we apply here, we'll just talk about positive ionization. So we're applying that positive charge to our analytes of interest. And we're doing some evaporation to try to separate our solvent molecules. So if we think about that spray, right, we have these big droplets, and the droplet contains our analytes of interest, things we're not interested in, things that didn't pick up a charge, our mobile phase, and we really want to separate that because we're only interested in our ions of interest. So we want to pull those ions of interest through our mass spectrometer. That way they would be introduced and we can do some experimenting with them. So all electrospray ionization is doing is helping us get that ion in a charged state so we can now pull it through our mass spec. But there's some important things to consider, particularly with ESI. We really want to think about our charged state. For some of these larger compounds, you'll notice that they'll end up in different charge states. So you might end up with a charge state of 10, for example. And then we also want to think about the ability of that spray to move through our mass spectrometer. Some of the things that we'll consider during the method development stage would be what ionization type to use. So right now, for all my examples, will be in positive mode because it doesn't really make a difference in terms of theory. But when we get into the method development section, that's where you might decide, hey, negative ionization is really how I'm going to get this compound to move through my mass spec. So just a quick example of a compound of interest. This compound has a mass of 146. If we're doing our positive ionization, here we would see a mass of 147. So we're adding a +1 in this case, versus if we had a doubly charged ion, we'd see this divided by 2. So instead of seeing a 147 or a 148, because it's 2 of the hydrogens, we'd see a 74. So when you're dealing with some of these larger molecules, things like proteins and polymers, understanding charge states is really crucial because you're going to need to know what mass to look for. But now that we've introduced our analytes, we can really get into the mass spec portion. So this is where we get to do the real mass spec. And at first, I'm going to be talking about quadrupoles. So quadrupoles were invented in the 50s by 2 German physicists, and we've been using them ever since because they're really good at being mass filters. And the way they work, without going into too much of the physics or too much detail, is that we have 4 poles, right? So hence quad. And these poles have different voltages. So they have different RF and DC voltages. And we're constantly changing those voltages and alternating them. So we have 2 A poles and 2 B poles. But our whole purpose in doing so is to keep the ion that you're interested in. Let's hypothetically say you really care about a mass of 500. So you want any ion with a mass of 500 or M over Z with of 500 to move through that quadrupole. So what the software and mass spec is essentially doing is applying voltages to do that. So you filter out those other ions that you're not interested in and really only retain that one interest or that one mass that you care about. So if we look at a little schematic of how that's working. So here we have our positive ions, they're moving through our triple quad. So we've got our Q1 acting as the first mass filter. So these are all ionized using ESI. They're being pulled through our first quadrupole. If we told the quadrupole to focus and filter out anything that's not 500 m/Z, everything else would fall out, and then it would be introduced into Q2. In Q2, you'll hear people refer to as collision cell or Q2, and they're both the same thing. You can use those terms interchangeably. It's really just referring to where sort of that fragmentation happens. So instead of starting to use this quadrupole as a filter, here we're going to be applying some energy to create something. And in our third quadrupole, that's where we're going to return to using that quadrupole as a mass filter. So if we take a second just to think about that selectivity, we have sort of a first mass, we're doing an experiment to the second or to that mass, and then we're filtering it again. And that's where we kind of get into some of this fun. So just a little brief about the background, but let's talk about the questions that we can answer, because that's the most exciting part about mass spectrometry, at least to me, are the questions that we can answer using it. So we've got our ions. Let's do our first workflow. Maybe we want to do just some traditional quantification. So regardless of whether you have a triple quad or a Q-trap, this experiment's going to work the exact same. You wouldn't notice that you used a Q-trap over a triple quad unless you happened to look in the metadata or peeked over at your instrument and saw that there was a badge on it that said Q-trap. So what is it? What is an MRM experiment? So MRM, multiple reaction monitoring, sometimes people just refer to it as MS-MS. Here we are taking a parent or a precursor, and we're selecting that. We're focusing on that parent or precursor and filtering out everything else. You'll often hear people refer to it as a parent, and precursor, interchangeable. Parent is a little bit of an older term. Typically in literature, you see it referred to as precursor now, but they both mean the same thing. So we focus on some parent, and then we're doing some fragmentation. So that's all taking place in that second quadrupole where we're creating something. So we're using energy to essentially, I like to say, bust that compound apart into fragments. And a fragment or a daughter ion is what's produced. And then in our third quadrupole, we're going to be filtering for a specific fragment or daughter ion. And again, daughter ion fragment, you can use interchangeably. Daughter is just a little bit of a more, an older term. So what does that experiment actually look like? So here we have our quadrupoles. We've got Q1, Q2, Q3. So in this experiment, I'm only interested in that compound with an M/Z of 215. So I'm going to use my first quadrupole to filter out everything else and only allow my 215 into my collision cell. In my collision cell, fragmentation is going to take place. So I'm going to fragment. So here I've got 4 fragments I could choose from. And again, in our next session, we'll really talk about how to choose these fragments and how to optimize for these fragments. But in this case, I'm going to select my 185. So using my Q3, I'm going to only allow that 185 to reach my detector, where I'll then get my intensity, and then I can decide to use that for my quantification, right? So that sounds great, but maybe it seems like a little bit of overkill to you. Why not just use the first ion, that 215? Surely that should be selective enough. And in some cases it might be, but in a lot of cases it's not. And I've got an example here from some data I worked on with a customer. So this is actually an algae protein powder. It was pretty delicious. I didn't taste it, but they were looking for pesticides in this algae protein. And they were looking specifically for MGK-264, which is a pesticide. There are 2 isomers of this pesticide. So if we look at the green box, we see those 2 beautiful isomers. Everything looks great. But if we go one over to the matrix blank, so this is just the straight algae powder with nothing in it, we see almost two peaks that look exactly like our pesticides isomers. They are at different retention times slightly, but if I was an analyst in a lab, I would have a really hard time being confident that that wasn't actually MGK264, especially with those two isomer peaks. And because of the sample, we knew it was a clean sample. So we went ahead and spiked it, and we saw our pesticides appear. But again, going back to our LC section, we didn't have the chromatographic resolution to separate them from that interference. So we end up with this kind of odd backwards L integration. I'm not super confident. I know that value isn't going to be very accurate, since I don't have my nice Gaussian curve. I don't really feel good about this data set when I'm just using my MS data. So we looked at our MRM experiment, and what we see is completely different. So we've got our standard again, but then in our matrix, we don't see anything. So that's telling us that just using the MS experiment, we saw those interferences, right? So those interferences had the same parent mass as the compound we were interested in. So likely they had a very similar formula, but they weren't that compound. So the structure was different, although the formula and parent mass were likely fairly similar. But using our MRM data, we can see, oh, well, the fragment didn't form, there's nothing there, and we get these two beautiful pesticide peaks in our spiked sample that we can then integrate and feel really good about in terms of quantification. So the benefits in our MRM data, it's really about the selectivity, like we showed, sensitivity, and it's a fast experiment. So, I talked about having the chromatographic resolution, which is really important. You saw that with the matrix interference, but because these experiments, an MRM experiment is so selective, it's okay if you have overlapping peaks because they're looking for completely different things. So that allows you to have these really large panels. So here's an example of, I'd say a medium, maybe small medium panel of 81 compounds. Go medium. And you can see that we have some peaks superimposed, but they're looking at completely different experiments. So we're not worried about it. And in terms of how long these experiments take, typically on the low end, we're talking about around 10 milliseconds for dwell time. But obviously we'd like a little bit more. So if you can keep it around 50, you're usually in really great shape. But if we think about how many experiments you can do in a second, if each one takes 50 milliseconds, right, it's a lot. But what are some of the other questions you can answer with an MS-MS experiment? So these experiments are going to be unique to Q-traps, just as a heads up. So the only difference really between a Q-trap and a triple quadrupole is that Q3 region. So Q-trap, right, quadrupole trap, everything up until that Q3 is exactly the same, operated in the same way. And then we have this trap. I like to conceptually think about it. I grew up lobster fishing. My grandpa was a lobster fisherman, so I spent a lot of time doing that. So conceptually, when I was introduced to the traps, that's just how I envisioned it. And I'm sure that would break some R&D scientists' hearts. But it kind of works the same thing in terms of just explaining. We're really trapping the things we care about in that trap and letting the other things that we don't care about leave that trap. And instead of doing it with nets and ramps, we're doing it with voltages. So what we can do is we can do some really cool experiments that we couldn't do in just a traditional quadrupole setting. So one of those experiments would be when we need to be highly selective. So how could we be more selective than an MRM experiment? Well, we can do MRM cubed. And just like it sounds, we're taking a parent, we're going to a daughter, then we're going to a granddaughter. Or we're taking a precursor, we're going to a fragment, and we're fragmenting it to another fragment. So we're being very, very hyper-specific to a specific compound structure. But what does that experiment look like? So here, we're going to do the same thing. We're focused on that 215. So we're going to select that mass of 215 and pass it through our quadrupole. And we're going to do our fragmentation in Q2. But this is where it's a little bit different. Here's where we start to use that trapping function. So we're going to select an ion of interest, again, that 185, and we're going to trap it in our trap. Once we've isolated it, we're going to go ahead and fragment it even further. So now we have the creation of these granddaughter ions. And from there, we can focus on a specific ion. So in this case, we'll look at the 133. So what type of scenario would this selectivity even be needed? Because maybe it seems like a little overkill right now. And there are two that I can think of that I use all the time. One would be in cannabis. Again, cannabis is a truly horrible matrix from an analytical standpoint. And the other would be looking at THC in hair. Another one of my least favorite matrices. It's complicated and it kind of just grosses me out, to be honest. But cannabis is it's a tough plant matrix. We have high concentrations of cannabinoids. We have all of these plant metabolites. It can be really challenging to look for pesticides in this matrix. So here we have an example of cyclothrin. So this is a pesticide that contains 4 isomers. So that's why you see those peaks. Again, it's going to depend a little bit on your chromatographic resolution, whether you see all 4 or if you just see 3. But we need to see this compound in cannabis at 10 parts per billion. And up top, we have a matrix blank, which has an interference that looks a lot like cyclothrin. And down below, we have a spiked 10 ppb sample. So we can see, obviously the intensity has increased, but I'm definitely not confident that that is truly cyclothrin. So if we use a MRM cubed experiment, all of a sudden we start to see, oh, in our matrix blank, we don't see that interference. So that's telling us, hey, by being even more selective, whatever compound had this interference or looks like cyclothrin, the structure was a little different. The fragment was a little different. So we didn't have the exact same fragment. So when we fragmented that fragment, we ended up with a different result. And that's why we have this clean matrix blank. But in our spike sample, we all of a sudden see this nice peak. And that's what we're really looking for. And that's where MRM to the cubed can be really valuable. But what if you don't want to just do quantitation? What if you want to do qualitative studies and quantitative studies kind of at the same time? And I have a bias. This is my personal favorite workflow with the Q-Trap when we do some multi-targeted screening. So here we're going to do an MRM experiment just like before, except we're going to follow it up with an EPI experiment. And this is called an enhanced product ion experiment. So we're going to be looking at fragmentation, and we're essentially after the compound's fingerprint. So that's what we're trying to get after. What does this look like? So for an MRM EPI experiment, we'll start out with our MRM experiment. So here we have an XIC. So we've got, again, that extracted ion chromatogram with all our peaks. And we apply some sort of intensity threshold. And we're looking for a compound that passes or surpasses that intensity threshold. If the compound doesn't, like that compound in the dark blue, we'll just move on to our next MRM experiment and continue down the line. If it does meet that threshold, what we'll end up doing is our EPI experiment. So here is where we're going to create fragments and essentially read them out to get the compound's fingerprint. What does that look like in real life? Well, in animation. So again, let's focus on that 215 ion. So we're filtering out everything else. We're creating fragments in that Q2. And here we're going to do something a little different. Instead of just using a single collision energy, so the voltage we use to create fragments, we're going to actually use 3 collision energies. And the reason we're doing this is to create a wide range of fragments. So we want as many unique fragments as we can get. So this is a nice way of doing that. Past there, we're going to allow those fragments to fill up the ion trap and then be read out by the software. And as those exit, they'll reach the detector and we'll get their masses. And this will give us the compounds, I like to call it again, fingerprint. So when would you ever need to do this? So this is another example of a sample a customer gave me. This was a powder. It was a supplement powder from a certain type of grass. And again, they need to look at it for pesticides. And what we saw in their grass sample, even in the blank, was this compound that looked a lot like phenoxycarb. So it had a peak shape that was great. It even had a secondary MRM that looked really close. So it made the ion ratio between the first MRM and the second MRM very similar to the standard. The only clue that this wasn't phenoxycarb from our MRM experiment was simply that it had a different retention time. But again, not a hugely different retention time. It was about 12 seconds. So maybe my column is just getting a little old, or maybe there was something different about this injection that caused a little bit of an earlier retention time. Again, this 12 seconds would be a cause for concern. Usually we like to keep it plus or minus 6 seconds, but still, me as an analyst, I'm not overly confident that this isn't phenoxycarb. I surely wouldn't want to make a mistake and have this batch go out to consumers who then would consume what appears to be a large amount of this pesticide. So we did our EPI experiment. And from our EPI experiment, that's where we realized, okay, up top we have our matrix blank, and then on the left or right-hand side, we have our fragmentation pattern. So this is our compound's fingerprint. And if we look down below for phenoxycarb, those fingerprints don't match at all. So not only do we have the retention time difference, but we have completely different molecular fingerprints. I'm happy. I will go stand up, write a report, do anything. I'm 100% sure that whatever is in that matrix is not phenoxycarb. I don't know what it is exactly. I could go back and search some libraries and try to figure it out. But for the purposes of this customer, they just needed to know that it wasn't phenoxycarb. So although mass spectrometry kind of seems like it would be a pretty easy thing, at least in television, there are a lot of steps to it. And we'll talk about those steps in the upcoming sections, but this kind of just gives you an idea of what to expect. When we think about LCMS, we want to think about separation. So we're always kind of focused on getting the separation chromatographic resolution for our compounds of interest. But really the question we always want to ask ourselves is, what question are we trying to get out of our data? Are we trying to be quantitative? What analytes are we interested in? That's really going to affect everything we do in the method development section and everything we do in how we process the data. So with that, I want to thank you very much, and I can take any questions.
Thank you so much, Carl, for the insightful presentation, and thank you for participating, and I hope you really enjoyed the content. And I'm going to go ahead and start with the first one, Carl, which is around mobile phases. You mentioned that you sometimes include additives, specifically acids, and why do you include the additives? And if you are going to include an additive, how do you select which additive is best for your application?
Yeah, absolutely. So great question. And actually, I have a couple of slides in our next presentation on this topic specifically. So I encourage you to check that out. But why are we adding additives at all? So we're adding additives essentially to change the pH of our mobile phase. And in doing so, we help ionization. There can also be a couple of different tricks that you can use that aren't just changing the pH. So one of the things I like to do, again, my background is environmental. I did a lot with polymer analysis. For polymers, the ammonium addict is way more intense than our plus H or sodium addict. So I always like to add ammonium formate because that helps promote some ammonium addicts so I can actually see the compounds that I'm interested in at a higher level.
Excellent. Your comment on adducts really drives into the next question. So if you're having a problem with sodium adducts, how can you reduce adducts? How can you reduce particularly sodium adducts? And they asked, would new glass bottles help, or is there cleaning techniques that should be utilized in order to reduce adduct formation? Yeah,
sodium adducts can be tricky to get rid of, right? And you hit the nail on the head with the glass. So it could be coming from your glass. Another thing I would encourage you to try to experiment with a different source from your mobile phase that you're using for your aqueous. So for example, if you're using like an in-house DI water, maybe try, if you have Millie Q or gold star would be to go and get some HPLC grade, MS grade water from somewhere like maybe Fisher or Sigma, and give that a try and see if that can reduce some of the sodiumatics you're seeing.
Excellent. The next question is around pressure. You talked about the pressure traces specifically for mobile phase A and for mobile phase B being seen. And can you comment on what you might anticipate as you increase your organic composition? What pressure change might be expected? And is that variable between types of organic mobile phases, like if you're using acetonitrile versus methanol?
Yeah, great question. I saw that question in the chat, and it makes sense. You're absolutely right. Your pressure would be less with something like an acetonitrile or methanol, but the way I was showing it was just the pressure read back from that one pump. So the way I had the pump set up was there are two binary pumps, so each has their own pressure. So that's why you see this increasing amount of pressure from pump B, even though maybe your total pressure is going down. So hopefully that kind of answers your question.
Great. Now we're moving on to some mass spectrometry questions from some chromatography-based questions. What if you don't know the parent ion that you would like to generate an MRM type of analysis on? What strategy should you use in order to determine, and can you create an experiment, a mass spectrometry-based experiment, without knowing the precursor mass or parent ion before?
Yeah, good question. And again, we'll go over that for sure in the method development section. But there are a couple of approaches you can take, and it really depends on the question you're trying to answer. So if you're trying to quantify something, presumably you have a standard for that. So the easiest thing to do would be to go ahead and infuse that standard, and then just do an experiment where you scan for sort of a predicted mass range. And we'll talk about in the next session how to define that predicted mass range. But a simple example would be if you know your standard has a mass of 500, you would set your first quadrupole to look for from 495 to 525 to make sure you account for somatics, and also you see as many forms of that compound as possible. That being said, on the other hand, if your question was more into I have this unknown sample and I don't know what I want to look for, with the Q-trap, you could do some unknown screening where you're essentially kind of doing the same thing that I was talking about with your MRM experiment, except you're using the trap to enhance some of the ions around, and then using that intensity threshold, just like before, to do your MSMS experiment. And it will do that based on whatever feature it sees that's above that threshold.
Excellent. A next similar question around choosing the best precursor ion. What if you have a protonated molecule and a couple of adduct formations? How do you select which particular ion you should use as your precursor ion?
Yeah, again, I'm excited because this means that the next session is going to be really good. So the way I do this is I choose them all. And I choose them all initially until I get into a matrix. And I think what you'll find is that different parents may have different interferences that you don't experience with, say, an ammonium addict. You see it with a plus H or a sodium. So until I've run my sort of spiked sample in my desired matrix, I keep them all there and then choose the best one afterwards based on intensity usually, or signal to noise.
Excellent. The next question is around the fragmentation. You may get multiple fragments from a precursor ion. How do you choose what out of the different fragments that you get you want to take on to use in your final methodology?
Yeah, and it goes to the same point. I would choose them all. Well, within reason, right? If there's 15, probably not 15, but I'd choose at least the top 5. And if you're working with a particularly challenging matrix, maybe something like serum or some sort of environmental matrix or blood, choosing them all and then spiking them into the matrix that you want to actually analyze is typically the best way I've found. And then using that signal to noise to decide which ion gives you the best sensitivity.
Excellent. I can tell everybody who's joining us today is really going to benefit from the next session as well. So I really am excited for you guys to sign up and join that. The next question is around chromatographic resolution and what is sufficient or appropriate chromatographic resolution and chromatographic separation for when you're utilizing MS-MS, and how do you balance those two?
Really good question. And it's definitely something that is going to depend a little bit. And I know that's a tough answer to hear, but it's going to depend on what you're kind of experiencing. So typically, if you're dealing with sort of trace level compounds, having your MRM superimposed isn't really going to make a huge difference. But if you're dealing with compounds that are in high abundance, what you can have is some suppression occurring. So because you have two compounds at high abundance coming out at the same time, you can only ionize so many things at once. And you'll notice that you'll have some source suppression. So we see it all the time with PFAS analysis. Once the concentrations get too high, we have some suppression. So we have to make sure our chromatogram is spread out sufficiently so that we don't experience it. But when I do my trace pesticide analysis, that's no longer a problem. So I'd say it's going to depend a little bit on the levels you're after.
Excellent. We have a question around the EPI analysis using the Q-trap technology. How do you select the appropriate collision energy when you are utilizing an EPI which looks at more than one fragment?
Good question. So the default for SCIEX is 35 volts, which that usually works really well for most small molecules. But as you get into some of these higher molecules things, or higher weight things, sorry, maybe you're doing some polymer analysis, 35 might not really produce any fragments for you. So you might need to increase that. So typically what I would do is start with 35, and then for the three collision energies, it would be plus 15, minus 15, and usually what I do. And simply because that matches the library that I use, which is the SCIEX library. But if you're interested in some of these larger molecules, it might be worth playing around with the collision energy and increasing it. So usually as you deal with larger and larger molecules, you'll need to increase the collision energy as those molecules get larger.
Great. The next question is around matrix effects. How does different matrix and different matrices impact ion production and ion efficiency?
Yes, the answer is a lot. And this is where we'll have to rely on a few different mass spec tricks and then a few different chromatographic tricks to help to deal with those issues. So like the previous question was asking about chromatographic resolution, that's one way to deal with a nasty matrix. So separating out some of those interferences is one approach. From a mass spec standpoint, we didn't talk about it today, but there's a variable called declustering potential, which should be specific to your parent molecule that you can adjust to try to remove some of the things you're not interested in and keep the ion that you truly are interested in terms of keeping the sensitivity as high as possible. And the last thing I would kind of encourage is those MRMs. Likely you'll see different suppression on different MRMs. So you might want to go ahead and just try, even though it might not be the most intense MRM, you might experience less suppression on that MRM.
The last question we have time for today, Carl, is around EPI methodologies. We have a question on, is all the different Q-trap instruments available? Do they all offer EPI analysis capabilities?
Yep. Yeah. So if you have a Q-trap, you have that functionality.
Again, I want to thank you, Carl, for the insightful presentation. I want to thank all of you for spending the last hour with us. We really hope it was informative and insightful for you as you grow your mass spec expertise and knowledge. So again, stay safe, stay healthy. Thanks for joining us, and we'll see you soon. Bye for now.